galvanizing. After a few years, if it's a very humid environment, it'd be gone completely. If it's almost dry, then it's good forever. So it makes the difference between, even appliances, a lot of things will just be electro-galvanized because they're only supposed to have maybe get wet a few times at most. If they continuously humid, eventually you completely expense the protection. So that's an example of getting completely the zinc out. You have a hole here, and I drew this type of connection before where you have this sheet either being held by the primary structure or holding the final cladding. Yes?
Can you get hydrogen embrittlement electroplating?
Yeah, you get hydrogen. That's a good point. It will come out normally down the road when you go do your heat treatment. The other thing about hydrogen embrittlement is if you have a soft steel, it's a lot more resistant to it. It will be able to take a lot more of residual hydrogen than a high-strength steel. So for sheet metal, it's relatively thin. The hydrogen is such a small atom that in a few weeks it'll be gone as well, just by that process. So when people, obviously there's always a risk to have it from manufacturing, but a lot of times it will come through service. It's just the reaction, those reaction of the zinc protecting the steel. If the environment is a little bit acid and you have the right chloride content in a certain number of conditions, will regenerate new hydrogen. And that's a reason why there's only a certain strength that you can put galvanizing on fasteners. The higher strength bolts for structural application, you can't galvanize them. And there are some that you can, but under a certain situation, if you use the designation is a A325 bolts. These are very common in buildings, and they come either straight or galvanized. If you use the galvanized grade, there's some conditions where we've seen them susceptible to hydrogen embrittlement. So here, if you look at that black line, this is a cross-section looking just outside. So this is the whole area. This is where the zinc started to be as it was out of the factory. So in that cut view, we have the steel, we have the hole, and I'm not going to do the thread just for the interest of time. So this is where the fastener is connected. So you have the steel here. So think about a droplet of water that will cover that area here. And then eventually it's another one. So it's not connected too far. So right here is where you still have your original zinc layer. So in terms of protecting all these surfaces, so you're protecting the damage you've done to the threads of your fastener by inserting it. And then you take the fresh area here. The only zinc you have to protect this is what's around the hole. So it actually can give you some idea, based on how much you've consumed so far, how much more life you've got if you continue to consume the zinc at the same rate. It's only a limited supply, and it wouldn't matter. And that's something I really want to emphasize. Even if I put a lot of, like a big zinc or magnesium sacrificial anode somewhere else, if they're not connected to an electrolyte, it's not going to work. Just a schematic of the hot dip galvanizing process. All right. The cathodic protection, we talked about it a little bit yesterday. This is just a bond wire. This is intended to connect two pieces of steel. Because essentially, if you're looking, this was the church, the first Church of Christ Scientist on Mass Ave. You see it at night because there's a lot of light out there. Just downtown Boston along the Massachusetts Avenue. One of the issue there was the wood piles were there for a very long time, but they were deteriorating. And the only way to really bring something in locally and doing all the work was with steel. It was the most efficient way to drive steel all the way to the to the primary to the rock and build it up, and that involved welding, all sorts of things going on. So at the end, what they had to do is connect all this steel together and put a bunch of anodes in the ground and let it be. You know, if it's a permanent anode, you have to apply a rectifier. You have to apply a voltage. You put a rectifier, and that was the case because they wanted a very, very long life. It's just a special project requirement. They were not thinking 25, 50 years. I think the last maintenance had to be in 50 plus years or something like that. Now, this ties into a lot of the discussions we had so far. You'll see diffuse. So this used to be just a rectangular section on each side for the braze alloy, but it didn't fuse the interface. So you melted, but you didn't bond to the steel well, and they were coming off just like that. So we had to do a hammer test on all the connections after the fact because there was only so much redundancy that they were willing to allow in terms of wire going in the basement from one place to the other. There was some redundancy, but not a whole lot. So it does point out to, you know, this system is relying on connections, and if your rectifier goes off 1 year and nobody takes care of it, then you start consuming your piles and all the connections that come into it. So it's a system that does require you know, a size that's big enough so there'll be some building engineers that will keep track of current consume every year and just make sure the whole system is working and monitor it. That's why it's using pipelines. Pipelines is just really, really large installation with a lot of qualified personnel to figure out what's going on. With a building, sometimes it could be a problem again because time goes on and say, oh, we have to do this inspection. Yeah, why? You know, and then things don't get done. So this is just a view. This was out of another project. That's all you need. If you have zinc or magnesium, you have all the wires coming into this little access hole, and you make your connection, electrical connection between them, and it's the soy that makes the electrolyte connection in there. So you can't put the anodes too far. You have to put enough of them that they are within interaction distance. And if there's any reason why there'll be a dry area between where you put the anode and your structure, it's just not going to work. So very dry soy is great for corrosion rate. It's really difficult in terms of protection if you really want to go in the protection route. All right, we got a little bit of time for stainless steel. I'll do it very briefly. Stainless steel will corrode. This example here is a big pressure vessel. As you can see, it's got some stain, but it's localized. So what happened, it got contaminated. If you manipulate stainless steel with regular steel, you're going to have some material transfer, and that's what's going to corrode. And there's a test here. You see that the oxide turned clear. I had to clean it up first, and then I use a special solution that shows up regular steel. We call it, yeah. And essentially, it's not a big issue in terms of material loss, but it doesn't look good. So stainless steel, you have to be careful when you're handling it. This is a more severe issue, these plates. You can see one side wasn't worked on. They were using beads to make a special finish of kind of a satin finish of the stainless steel. But the beads were so small and provided at high energy, this hasn't been exposed, that it was creating holes, and it was remaining embedded on the surface, and that caused the initiation of the pitting reaction. And then from there, it just starts bleeding to a macroscopic side. This is the same thing here, where you have a lot of mechanical work to make that brush finished on stainless steel. Looks great, but in terms of the corrosion resistance, it's reducing it, because now you have a roughness. You already have preferential sites to start the pitting reaction. This is probably the key concept where different alloys chemistry in stainless steel will give you a more or less resistance to pitting corrosion. And that's just about trying to initiate the anodic reaction, just becoming and continuing in that area is dependent on how much chrome, how much nickel you have. And it's unfortunate, but it's the truth that the more money you pay for your stainless steel, the more resistant it's going to be to that pitting corrosion. And I've used this graph a lot in terms of determining, okay, so I may have salt water. This is going to be my highest temperature. I want to make sure I'm not getting into this zone. So there are a lot of those available. It doesn't even have 3 or 4. So this is for when you're really serious about it. So if there are some stainless steel that just won't really resist chlorides. The 410 stainless steel is just got chrome in it, the minimum amount of chrome, and if you try to use it even for a handrail and somebody is using de-icing salt, it's going to become really bad and very quickly. 304 can be the same. 316 now you're starting to talk about, and it's still available. So if you really expect any chlorides, I would suggest to start around 316, but not think that it's definitely going to work. There may still be issues. So you can see here, depending on your temperature, at ambient, it would take 1,000 ppm chlorides, but you go up in temperature if you're exposed to the sun or if you have a heat source, and then all of a sudden your resistance goes down. This plot, and a lot of these things are the same way. They're just nominal values. If you have this bead blasting process, if you have the brushing, it goes down. There's no absolute value here. It's only based on a certain nominal roughness and mill finish normally. It depends on how the test was conducted, but it's not an absolute value. It's more an indicator, and then you have to work from there and see, specifically what could have happened. So I hope that you get the idea that a lot of different corrosion processes will take place. There are ways to control. It's very hard to completely avoid the reaction of the metal with the environment. It wants to go back to where it was, but you can control that reaction. So the coatings essentially defer the penetration of moisture and oxygen. Galvanizing is using the sacrificial material or a current for permanent anodes. The inhibitors are applicable for closed system. And I think for stainless steel, you have some idea about manipulating it, and adding regular steel to it is a problem. Pitting is a problem. Typically comes with chlorides and either surface finish or just chlorides, or chlorides and temperature, depending on what the situation is. So I had to rush a little bit in the end. I'm sorry. That's what I had today. Any questions?